calculate line loss, which is essential for determining the appropriate wire gauge in electrical systems, let's examine the formulas and factors involved for both household and low voltage scenarios. The formula for calculating line loss in kilowatts is the same for both 120 volts to 240 volts household current and 12 volts low voltage systems, and is expressed as line loss in kilowatts equals voltage in volts times current in ounce times length in meters, all divided by 1000 times conductor resistance in ohms per meter. To use this formula, you need to determine the conductor resistance, which is calculated using the formula conductor resistance equals resistivity in ohms times millimeters squared per meter times length in meters, all divided by the cross-sectional area in millimeters squared. Let's define each of these terms. Voltage in volts is the voltage of the system, either 120 volts, 240 volts, or 12 volts. Current in amps is the current drawn by the load connected to the circuit. Length in meters is the length of the wire run from the power source to the load. Conductor resistance in ohms per meter is the electrical resistance of the wire per unit length, which depends on the material and size of the wire. Resistivity in ohms times millimeters squared per meter is the specific resistivity of the wire material, typically copper or aluminum. Cross-sectional area in millimeters squared is the cross-sectional area of the wire conductor, which determines its current carrying capacity. Now let's discuss how to determine when to increase the wire gauge. To determine when to step up to a larger wire gauge, compare the calculated line loss to the allowable power loss for the wire. The allowable power loss is typically specified as a percentage of the wire's rated ampacity. If the calculated line loss exceeds this allowable limit, a larger wire gauge is required. As a general guideline for household current, voltage drop should be less than 3%, which is acceptable for most applications, and power loss should be less than 5%, also acceptable for most applications. For low voltage systems, the acceptable power loss depends on the battery capacity and load requirements. Factors to consider include battery capacity, load requirements, and the sensitivity of the connected devices to voltage variations. Now let's elaborate on the concept of resistivity. Resistivity is an intrinsic property of a material that quantifies how strongly it resists the flow of electric current. A low resistivity indicates that the material readily allows electric current to flow, while a high resistivity indicates that the material opposes the flow of electric current. The unit of resistivity is typically expressed as ohm meters or ohm millimeters squared per meter. Different materials have different resistivities. For example, copper has a low resistivity, making it an excellent conductor for electrical wiring. On the other hand, materials like rubber or glass have high resistivities, making them suitable as insulators. Temperature also affects resistivity. In general, the resistivity of most metals increases with increasing temperature. This is because high temperatures cause increased vibrations of atoms within the metal, which impede the flow of electrons and increase resistance. When calculating conductor resistance, it's important to use the appropriate resistivity value for the specific wire material and operating temperature. Tables and charts provide resistivity values for various materials at different temperatures. Next, let's discuss cross-sectional area. The cross-sectional area of a wire conductor is the area of its cross-section when cut perpendicular to its length. It is typically measured in square millimeters or circular mils. The cross-sectional area of a wire directly affects its current carrying capacity. A larger cross-sectional area allows more electrons to flow, reducing resistance and increasing the wire's ability to handle higher currents without overheating. Wire gauge standards, such as the American wire gauge or AWG system, specify the cross-sectional area of wires. Smaller AWG numbers correspond to larger cross-sectional areas, and vice versa. For example, a 12 AWG wire has a larger cross-sectional area than a 14 AWG wire and can therefore carry more current safely. When selecting a wire gauge for an electrical circuit, it's important to consider the current requirements of the load and the allowable voltage drop. A wire gauge that is too small for the current can overheat, leading to insulation damage, fire hazards, and voltage drop issues. Now let's elaborate on voltage drop. Voltage drop is the reduction in voltage that occurs along an electrical conductor as current flows through it. It is caused by the resistance of the wire, which dissipates some of the electrical energy as heat. Voltage drop is typically expressed as a percentage of the source voltage. Excessive voltage drop can cause various problems, including dimming lights, reduced motor performance, and malfunctioning electronic devices. To minimize voltage drop, it's important to select an appropriate wire gauge for the length of the wire run and the current requirements of the load. Larger wire gauges have lower resistance and therefore result in less voltage drop. The acceptable voltage drop limit depends on the application. For household wiring, a voltage drop of less than 3% is generally recommended. For sensitive electronic equipment, the voltage drop may need to be even lower. Several factors influence voltage drop, including wire length, current, wire gauge, and wire material. Longer wire runs result in greater voltage drop, as the current has to travel a longer distance through the wire's resistance. Higher currents also increase voltage drop, as more electrical energy is dissipated as heat in the wire. Smaller wire gauges have higher resistance and therefore result in greater voltage drop. Different wire materials have different resistivities, which affect voltage drop. Copper has lower resistivity than aluminum and therefore results in less voltage drop for the same wire gauge and length. To calculate voltage drop, you can use Ohm's law, which states that voltage drop equals current times resistance. The resistance of the wire can be calculated using the formula mentioned earlier, considering the wire's resistivity, length, and cross-sectional area. Finally, let's discuss power loss. Power loss, also known as line loss, is the dissipation of electrical power as heat in a conductor due to its resistance. It is typically expressed in watts or kilowatts. Power loss is directly related to voltage drop and current. Higher voltage drop and higher current both result in greater power loss. Power loss not only wastes energy, but also can cause the wire to overheat, leading to insulation damage and fire hazards. To minimize power loss, it's important to select an appropriate wire gauge for the length of the wire run and the current requirements of the load. Larger wire gauges have lower resistance and therefore result in less power loss. Power loss can be calculated using the formula power equals current squared times resistance. The resistance of the wire can be calculated using the formula mentioned earlier, considering the wire's resistivity, length, and cross-sectional area. The allowable power loss limit depends on the application and the wire's rated ampacity. It is typically specified as a percentage of the wire's rated ampacity. For household wiring, a power loss of less than 5% is generally recommended. Now let's integrate these concepts into practical applications. Consider a household circuit with a 120-volt power supply, a load that draws 15 amps, and a wire run of 20 meters using 14 AWG copper wire. First, we need to determine the resistance of the wire. The resistivity of copper is approximately 1.68 times 10 to the power of -8 ohmmeters. The cross-sectional area of 14 AWG wire is approximately 2.8 millimeters squared. Using the formula for conductor resistance, we can calculate the resistance of the wire. Next, we can calculate the voltage drop using Ohm's law. Voltage drop equals current times resistance. If the calculated voltage drop exceeds the acceptable limit of 3%, we would need to step up to a larger wire gauge, such as 12 AWG, which has a lower resistance. Similarly, we can calculate the power loss using the formula power equals current squared times resistance. If the calculated power loss exceeds the allowable limit of 5%, we would need to step up to a larger wire gauge to reduce power loss and prevent overheating. For low voltage systems, such as a 12 volts lighting circuit in a vehicle, the same principles apply. However, the acceptable voltage drop and power loss limits may be different depending on the battery capacity and load requirements. Low voltage systems are more sensitive to voltage drop due to the lower voltage levels. Therefore, it's important to use larger wire gauges and minimize wire lengths to maintain adequate voltage at the load. In summary, calculating line loss involves understanding the formulas for conductor resistance, voltage drop, and power loss. It also requires considering factors such as wire material, wire gauge, wire length, current requirements, and allowable voltage drop and power loss limits. By carefully selecting the appropriate wire gauge for each application, you can minimize voltage drop, reduce power loss, and ensure safe and efficient operation of electrical systems. Always consult relevant electrical codes and standards such as the National Electrical Code or NEC for specific requirements and guidelines related to wire sizing and installation. The NEC provides tables and charts that specify the allowable ampacities of different wire gauges and the maximum voltage drop limits for various applications. It's also important to consider dirting factors, which may be required under certain conditions, such as when wires are bundled together or exposed to high temperatures. Dirting factors reduce the allowable ampacity of wires to prevent overheating. When in doubt, it's always best to consult a qualified electrician to ensure that electrical wiring is installed safely and in accordance with applicable codes and standards. Electrical work can be dangerous, and it's important to take all necessary precautions to prevent electrical shock and fire hazards. In addition to the formulas and guidelines discussed, several online calculators and software tools can assist in calculating voltage drop and line loss. These tools can simplify the calculations and provide accurate results, especially for complex circuits with multiple loads and wire segments. However, it's important to understand the underlying principles and assumptions of these tools to ensure that the results are valid and reliable. Always double-check the results with manual calculations and consult relevant codes and standards. Furthermore, consider the long-term performance and reliability of the electrical system. Over time, wires can corrode or degrade, increasing their resistance and voltage drop. It's important to use high-quality wires and connectors and to properly protect them from moisture and other environmental factors. Regular inspections and maintenance can help identify and address potential problems before they become serious. In conclusion, calculating line loss and selecting the appropriate wire gauge is a critical aspect of electrical system design and installation. By understanding the formulas, factors, and guidelines involved, you can ensure that electrical systems operate safely, efficiently, and reliably. Remember to always consult relevant codes and standards and to seek the assistance of a qualified electrician when necessary.